Hi again. In this second video I would like to cover the last part that we covered last year, which is going to be very useful for understanding what we are going to see in our two classes. And now we are relaxing the assumption that the models are stationary. Remember, with the VERs we were saying that the variables are stationary, the models are stationary, and we are not that worried anymore. But one of the problems that we have in time series econometrics is that the time dimension can change some things. It can affect what we call the order of integration of the variables. Okay, so if you remember from last year, we said that a variable is stationary when you don't need to make any difference, to take any difference, so as to make it stationary. Okay, it's stationary by itself, so we call them unintegrated of order 0, of I0. If they have a unit root or they are not stationary, that means that we have to take one first difference to make it stationary. Okay, and this first difference to make it stationary implies that the variable is integrated of order 1 or I1. What we want to do now is to test for that, how sure we are that the variable is I1 or I0. Actually we don't, and even with the tests we can never be, because the tests are approximations of, they are approximations to what we call the data generation process, which is unknown. Okay, so with these approximations we want to see whether the variables are stationary or not. Implications of knowing the order of integration. First of all, remember that if the variables are I1 and the error term or the residuals of the equations are, well, the error term is not stationary, then the t-statistics are not valid anymore, meaning that any inference based on the t-statistics or the p-values is invalid. The estimation is fine, it's just that we cannot be sure if the estimated parameters are significant or not. What is the intuition? If a variable is stationary and we give a shock with an AR model of the simple ones, we'll see that the variable changes temporarily and then it comes back to the equilibrium. Okay, but if the variable is not stationary, is I1, or it contains a unit root, if we give a shock to this variable and we plot the impulse response function or the MA representation, we'll see that it explodes, it goes up forever. So a shock has long memory effects. Okay, and this is very relevant for policy, because if the unemployment rate, for example, that by definition should be stationary because it's bounded between 0 and 100, but for some cases or for some periods the testing would tell us that this unemployment rate, especially for the case of Spain, it can behave as a unit root. So the government, knowing that it's behaving as a unit root, it has to apply different type of philosophy or different type of policies than if the unemployment rate is stationary. If it is stationary, that means that eventually we'll come back to the equilibrium. There is not much we can do. We can maybe accelerate it, but maybe there is not much to worry about. But if the variable does not come back to the equilibrium by itself, then we need to intervene. We cannot just let it go up forever, as it has happened. Is the COVID for the time being, is the COVID stationary? Well, it's clearly not stationary. I know that in Estonia things are much better than they are in Spain, but in Spain it's definitely an explosive process. It's clearly more than a unit root, I would say. Okay, very good. Oh, sorry, let me see if I can make this work. Very good. Okay, so stationarity and unit root testing is something that is quite relevant, and we are going to spend some time in understanding or remembering how this testing is done. Okay, it's what we call the unit root testing. We have two types of tests which are unit root tests, because under the null hypothesis we have a unit root, like in equation 1. This is what we call a unit root process or a random walk process, because as you have there, yt is equal to some constant which we call mu plus yt minus 1. The coefficient of yt minus 1 is 1, so we have a unit root. So that process is not stationary. The second process is, even though it has a time trend, we would observe if we plot it that the variable always come back to this trend, to this t, okay? But the fluctuations will be more or less constant along time. I'm talking about this one now. Although this is not the classical example of a stationary process, is stationary because it comes back to a deterministic trend, okay? So it could be, for example, the GDP. The GDP could be a stationary process around a trend. It should be a stationary process around a trend, okay? Very good. So you have there as well, the first equation is that if the idea is to estimate this parameter theta that we have there, okay, is this one here. This guy is going to tell us whether we have a unit root process or stationary process. Sorry, my finger is going away. Okay, so this one. As you have there, if you have that this theta is equal to 1, you have a unit root. If this theta is greater than 1, it's not very common, but for financial series it could be, and then it's explosive. So anything which happens in the time, at any moment in time, is going to magnify. The idea is basically to analyze what is the value of this theta. This is basically to show what I summarized at the beginning, the fact that a stationary process has only limited memory, okay? So if we basically rewrite recursively any R1 process, like equation 3, we write it recursively, what we have is this equation here, which basically is saying that we have a collection, but this could be that like the first observation, and then we have a collection of the previous error terms, but see that is the coefficients go from theta power 1, theta power 2, and so on, power 3, and the last one is power t. Now the important thing we have to remember, this is a collection of shocks, okay? So we are transforming the R process into an MA process. Now, does this have short memory or long memory? Well, actually depends on the value of this theta, okay? If theta is less than 1, 0 point something, the power of something which is 0 point something gets smaller and smaller over time. So we are saying that if we have a stationary process with a theta less than 1, 0 point something, that means that these numbers here would go smaller and smaller, and meaning that the farther in time we are talking about, the less important is the past. But if this theta is 1, observe that 1 to the power of anything is always going to be 1, so it's like it will always be there. This will be 1, this will be 1, and so on. So it has long memory. Whatever happened in the past, it will always stay in the present, okay? And that's the effect of a non-stationary process or a unit root process. This is basically what you have there. I'm not going to linger too much. So equation 1 is the classical non-stationary process, okay? We can transform that one into a stationary process by taking the first difference, and this is what we have in here, okay? So we take the first difference, is delta, and we define L as the lag. This L is the lag value of the variable. We can obtain this guy here, and basically this by definition is stationary. See that there is no y(t-1) here. When we have transformed it, it has disappeared and we have made it stationary. This is a constant is a constant, and this ut by definition is stationary. So a process which is a unit root or is not stationary, we can make it stationary by taking first differences. Now in practice we don't know if we have to remove this stochastic trend, this unit root, or we have to do something about it. So if we are sure that we have a stochastic trend, that is that the process is I1 is a unit root, we take first differences and it becomes stationary. If it has a trend but is stationary around the trend and we take first differences, we are making a mess, okay? The problem is that when we plot the variables. That's the only way to have an idea before we do the testing of whether the variable is stationary around a trend or is a unit root, is that more or less they behave the same way. We see that they go up, okay, and then we cannot really tell. And if we try to remove a deterministic trend, so a process which is stationary around the time trend, by taking first differences, we are screwing up the residual. So that's why it says here that using the right method is quite important. This is an example of just a random white noise process is something which is stationary. Okay, so it goes around 0 very fast. Okay, and more or less the amplitude or how big this volatility is more or less is constant over time. So this is a stationary process. Now we have a random walk and a random walk with a drift. A drift is a constant, doesn't matter, they behave the same way. So you see what we have, whoop, it goes up. Okay, this is a random walk with a drift. That is a unit root process. How do I know it's a unit root process? Because this is simulated. So we have simulated it with an equation which is a unit root. This, for example, is a stationary process around a trend. So you see that there is a trend. It obviously the amplitude of the variation also remains constant. So I mean, in this case we could say that yeah, it looks like it's a time trend, it's not a stochastic trend. So this process looks like stationary around a trend. Problem is that in practice, when we, as I said before, when we plot the variables, we don't know what they are. Okay, what is this? Well, this is basically just to show you different processes depending on this phi, or what I was calling theta before. It's actually phi. Sorry for my Greek, it's not very good. Okay, so if it's 0, it's stationary, it's a random walk, it's the yellow line. If it's 0.8, which is close to 1 but not close enough, it's also going around 0. But if it's a stationary process, if it's equal to 1, then you know the amplitude is quite wide. Okay, very good. I'm not going to stay here too long. It's just that we need to remember that well, this part here, no, yt is integrated of order d, and d is going to tell us whether it is stationary or not stationary. For today, for this video, we are going to consider d as 0 or 1. If it's integrated of order 0, for d equal to 0, process is stationary. If it's I1, d is equal to 1, is non-stationary, it contains a unit root. Okay, so basically this here is saying that a variable which is integrated, but general, no, that if it is integrated of order d, if you take d differences, it becomes I0. So in the example we have talked before, if it is integrated of order 1, you take 1 difference and it becomes I0. Okay. This I'm going to skip. How do we test it? Well, last year we talked about basic tests, the Dickey-Fuller test, which is in EViews or in any software. You just click the button, it estimates the model and it is telling you whether this, I think this Greek letter here is called psi. So if psi is equal to 0, we have a unit root. If psi is less than 0, is negative, then it's a stationary process. Okay, this is basically how they do it. It's a Dickey-Fuller test. Blah blah blah. How it is done? Well, it's basically the t statistic of this psi estimated. This is what we are going to look at. But the problem is that this I call it t statistic, but actually that's wrong. This test statistic, this looks like a t statistic, but it's not a t distribution. Okay, and it's not a t distribution because the t distribution is obtained by assuming that the error term is stationary, and that's what we don't know. Okay, so that's why Dickey and Fuller, these guys of the test, they actually they produce the critical values, but we don't have to worry about critical values because EViews gives you the p-value, and if the p-value is less than 0.05, then you have a stationary process, you reject the null. If the p-value is greater than 0.05 or 0.1, then the process is a unit root. Okay, so we continue. Augmented Dickey-Fuller is the same story, with just we are including lags of the dependent variable. Higher order of integrations. Can a variable be I2? Yes, in practice, yes, but we are going to pass because this is actually a big problem that not even the advanced econometricians know very well how to do it. So when the variables are I2, we just take or two differences or one difference and then we do cointegration. Okay. Phillips-Terron test is basically same. It's a cousin of the Dickey-Fuller test. It tests the same way. This is just using non-parametric methods, but we don't really worry too much about it. Then we have something which is the instead of testing for the null hypothesis of a uniroot process, we swap it, and you can have tests which are stationarity tests. Okay, you have here the hypothesis for the test is not that the process is a uniroot, it's the opposite, is that the process is stationary. That's what we call stationarity tests. The KPSS test, which again is on any software, is the one that you would use. Okay. You have here different options when you test. You use the two tests, the Dickey-Fuller or the Phillips-Perron, and the KPSS. So it is possible actually that they don't coincide, and one test is telling you the process is stationary and the other test is telling you the process is I1 or uniroot, and then you really don't know what to do. That's very common. Okay, so let's suppose that we have a bunch of variables. We want to see how they are related. We will do a VAR, but they are I1. We cannot just estimate a VAR. One solution: we take first differences of all of them and we estimate a VAR. Yes, but that means that we would only be seeing short-term relationships. If we want to see a bigger picture with short-term and long-term relationships, then we use cointegration. Cointegration, the idea is to get a linear combination of variables which are I1, but this linear combination is actually I0. So those stochastic trends, those uniroot processes, they cancel out among themselves. No, that is basically what you have here. That you have variables which are these x variables are ID, and then you combine them, and then the z is actually of order less than d. Bye. Okay. So I'm not going to linger too much here. Definition of cointegration, Engel and Granger. Well, basically, again, same story. You have a bunch of I1 variables, you combine them, and they become I0. Okay, that's the idea. And there are tests for that. So you can test whether there is cointegration between the variables. The basic tests are residual based, like the Engel and Granger test. So basically, what you do is you estimate by OLS the relationship between your variables. You get the residuals, and then you apply the Dickey-Fuller test over the residuals, and you see whether they are I0 or I1. If they are I0, there is cointegration. If they are I1, there is no cointegration. Okay. What happens if there is no cointegration? You may need to include more variables into your model to cancel out that extra stochastic trend that you have there. Or simply, if you cannot find more variables which make them cointegrated, you can just use first differences, but again, you don't have long-run relationships. You would be only looking at the short-run relationships. Okay, you have here like examples of cointegrating relationships. I'm not going to link it too much. Okay, so we can estimate. So if we have a cointegrating relationship, we can estimate a model which looks like a VAR with both long run and short run information. Short run information would be the first difference of the variables, and long run information would be this linear combination between the variables, which is stationary. That is what we call the long run or long term. Okay. Basically, equation 2 is what we call an error correction model. This is a basic error correction model. We are not doing any magic. So we have the first difference of one of the variables, okay, of xt, first difference, and then here we have what we call the cointegrating relationship. This stuff that we have here is the cointegrating relationship, is the cointegrating vector, and this gamma letter that we have here that we estimate is the value that makes this relationship cointegrated. So if we take the error term in this, my finger disappears, but if we take the error term in this equation, it should be stationary, because this is by definition stationary. If x and y are stationary, this is stationary because we take the first difference, this is stationary because we take the first difference, and this is stationary because it's a cointegrating relationship. Again, basic test for cointegration that we discussed last year. You just estimate a relationship by OLS, take the residuals and apply the Dickey-Fuller test over these residuals. If the residuals are zero, you have cointegration. Congratulations. If you find that the residuals are not stationary, the opposite to congratulations, you don't have cointegration, so you have to work a bit harder. Now, very good. Engel and Granger would say that this is the very basic approach, which we don't use at all, very much. So basically it says you just estimate your cointegrating relationship, you get the residuals, and then you plug these residuals in these residuals here. You get these residuals and you just plug them in another equation where you have the first differences, and that's it, that's your model. Okay? We don't use that because it has some issues, some problems. Let's forget about this. This is an example that we covered last year. It's basically to see the relationship between forward and spot values. So basically you can just estimate this equation, and then first the idea is that if this f and this s they are non-stationary, the idea is to find a cointegrating relationship between them. Okay. Basically this is the example, which I'm going to just skip, go through the next part, because the interesting one is the one we covered last year as well, is the Johansen method, which I believe you are an expert now using Johansen. And the advantage of Johansen is that if you have more than 2 variables, you can estimate up to n-1. If you have n variables, you can estimate up to n-1 cointegrating relationships. You cannot do that with Engel and Granger. You just estimate one combination, that's stationary, you move on. But in theory, if you have more than 2 variables, 3, 4, etc., you can have up to n-1 cointegrating relationships, which you should include in your error correction model, otherwise it's not well estimated, it has problems. Okay. So basically here what we have are matrices of the variables. Basically this is a VAR, but you can rewrite this VAR in first differences to make it stationary and include this guy here, which is a collection of cointegrating vectors. Okay, and this is what we call a vector error correction model. In some books you may see it as a cointegrated VAR. Okay, now the idea is to estimate all these models at once. So basically it has to do, how do we estimate these cointegrating relationships? Okay, first of all, how many cointegrating relationships we have? It has to do with the rank of this pi matrix that we had before. Okay, the rank is how many linear combinations, independent linear combinations we have in this pi matrix. That's what we do here. We use the eigenvalues. Again, I'm not going to go into the detail, but the idea is to first of all obtain how many cointegrating relationships we have. Once we know how many cointegrating relationships we have, we can use the eigenvalues, blah blah blah. An example here that we discussed last year, I believe, is that this rank is telling us how many cointegrating vectors we have. Once we know how many cointegrating vectors we have, then we can just estimate this animal here, which is what matters. Okay. What it matters, there are 2 tests, the lambda test and the trace test. You basically do it like one by one. You see if there is 0 versus 1, 1 versus 2 cointegrating vectors. No? 0 cointegrating vectors, no cointegration, versus 1 cointegrating vector. If you say that there is 1, then going to test 1 versus 2, 2 versus 3, and so on. Okay. Now, if you find that R is 0, that there is no cointegrating vectors, that means that they are not cointegrated. And the question I normally ask is that what happens if r is equal to n? So you have 4 variables and you have 4 contiguity vectors. We said that you could have up to n minus 1, not up to n. So is it possible that you click the buttons and it tells you that you have 4 variables, you have 4 contiguity vectors? Yes, it's possible, and the answer is that it's possible because that means that you have done something wrong before with the testing of the uniroots, because that means that the 4 variables are stationary. They are contiguity vectors by themselves. Okay, so be careful with that. Trace test, lambda test, don't worry too much. Again, this is basically how we do it. We go from 0 to 1, 2, and so on. Okay. Okay, so this is basically how you look at things. Important things that you have to remember is that also there is one thing that you can do with Johansen that you cannot do with Engel-Granger, and is that you can estimate or you can test whether there are some theoretical relationship between the contiguating coefficients. So you estimate by maximum likelihood the whole thing, okay, and then you have some contiguating relationships which you may not be able to say what they are, but you can use theory to test whether this relationship or this contiguating vector is stationary. And for example, in this case for the PPP, so we are relating nominal exchange rates with national prices and foreign prices. So the PPP theory says that those coefficients should be 1 minus 1 and 1. So you can test for that, okay? And that's quite useful. Also, I would like to say that yes, I would like to okay, let me go back to see if I can find yes, this one is important. Okay, so we have this alpha, this pi or p matrix, which is the matrix which we multiply to yt minus 1 or yt minus k to obtain the contiguating relationships. But they can be decomposed into 2 matrices with coefficients, the alpha and beta. Beta, the beta combination of the coefficients, so this matrix beta is telling us the actual long-run relationship between the variables, okay? And alpha is what we call the loadings, or is as well the speed of adjustment. Okay, so we are saying that we have a contiguating relationship that when it deviates from the equilibrium, it comes back to the equilibrium at the speed of alpha, right? This alpha has to be negative by definition, okay, because it's what we call an error correction thing, an error correction term. So if it's an error correcting thing, it has to come back. If you have a shock on your variables, this alpha, by being negative, is bringing it back. Important, when you estimate by Johansen contiguating relationships, this alpha has to be negative. Negative for the first variable that you have in your contiguating vector. Important, eh? So you have, I don't know, y, let's suppose that your contiguating vector is y minus beta 1 xt, okay? Yt or yt minus 1, y is your normalizing variable. So because you have a vector here, you have a vector like a VER. For the equation of y, you will have an equation for y, an equation for x, for the first difference of y and for the first difference of x. So for the equation of the first difference of y, this alpha has to be negative. For the other one, it doesn't matter. Or it matters, but we are not going to get too worried about it now. What you need to see is that this alpha is negative for the equation of the variable that you put first in your contiguating relationship, the one that you are normalizing for, okay? So if we go back just for a second, let me see if I can find the example I want to discuss. I guess I could edit, right, this is what I wanted. This this is with an error correction model with Enger and Granger, so we only have one equation. If we have a Peckham, we have two equations, another one for delta xt. And in any case, the equation for delta yt, you should have that is, here they put it because in the book in the Brooks book they call it beta 2, but in the world of Johansen is alpha. This alpha has to be negative. Why? Because the first variable that we have here is y. Okay, so we are normalizing for y, and for the equation of y, which is this one, this beta has to be negative. Okay, because again, a deviation from the equilibrium, it will be brought back by this loading or this alpha in the world of Johansen. Okay, from all this blah blah blah, important, remember what is a unit root, what are the implications of unit roots, how they are tested, what is the meaning of cointegration, how we do cointegration, and a little bit the interpretation of the Johansen tests. Okay, from here we will build the rest of stuff in these two classes. Well, I'm going to stop here. Thanks a lot for listening, and see you soon. Bye bye.